All right, thank you for having me. Thanks to the organizers for inviting me, and thanks to everyone who woke up to come to this talk. I myself, I'm not very awake yet, so I'll provide an overview of recent algorithmic progress on robust learning in high dimensions. So this is the question that we're going to try to address. So can we develop efficient methods for accurate estimation and inference in high dimensions when we cannot trust, at least not fully, the data that we have? So, I mean, this is like a classical question. I feel that maybe for this audience, I don't need to motivate it, but I'll still do it for a minute. I mean, this is like an old question of misspecification. So as we know, any model that we have is very rarely perfect. And this is not new. Fisher already knew this when he talked about parametric inference in the 1920s. And much later, scientists like Tukey and Huber, they formalized this question and they studied it more systematically from the statistical viewpoint. So this study led to what we now call robust statistics. And now from a more sort of modern motivation, we have sort of the question of outlier detection in high-dimensional datasets. For example, if you have a biological dataset, in many situations it has been observed that it comes with natural outliers that we would like to detect, if possible, and remove them when we do some kind of downstream statistical analysis. And the way this usually happens, at least so far, is by some kind of manual labor of the domain scientists, and this is not this is not viable as the scale of the problems increases. So we would like to have methods that are automatic and reliable for outlier detection in high dimensions. And finally, secure machine learning. So what is the idea here? The idea is that, let's say you have a machine learning system. The data of the system comes from the outside, from many users, and some of the users are malicious. Their goal is to sort of pollute the result of the learning process. So they insert carefully selected fake data into the system to compromise its behavior. And this is something that's standard in recommendation systems. Now let's switch gears and talk about the statistical learning setting. So this is a generic definition of statistical learning. So we're given IID samples from an unknown model that is promised to belong in a known family of models. And we want to approximately find the unknown parameters. And of course, when presented with such a question, with such a problem, the first question to ask is, can we do this efficiently? Where efficiently for primarily for statisticians means what is the sample size to like minimax. For computer scientists, it is also computational complexity. You want the underlying method to be computationally efficient, so polynomial time in sort of high level, but ideally also linear time. But in addition to these two criteria, there is a third one, which is the topic of this talk. And this criterion is robustness. So I'm going to define it in the next slide, but basically at the high level, what robustness does is that it challenges this assumption that the data that you observe are IID samples from an unknown model in a known family. So it's an additional performance criterion, all right? And ideally, we would like to, present with a given task, we would like to have an algorithm that is statistically efficient, computationally efficient, and robust, if possible. Or if not, we would like to understand the inherent trade-offs between these three criteria. Now, what is robustness? I'm going to focus on this definition for most of today's talk. So this is a model that we call strong contamination model. It is a strengthening of an old model from robust statistics called Huber's contamination model. So the idea is simple. So out of the data points that we observe, a small constant fraction are corrupted. We make no assumptions about them, so we call those corrupted points outliers. And the rest of the points are drawn from the model of interest, so they're called inliers. So you can see the formal definition in the slide. So it's a two-stage process. First, someone generates a set of clean samples, so IID samples from an unknown model, the model that you're interested in estimating. Then an adversary looks at those clean samples and arbitrarily changes an epsilon fraction of them. So this means the adversarial picks an epsilon fraction of the inliers, removes them, and then replaces them by arbitrary points. And now the final data set is the epsilon corrupted data set that we are given as input, and we want to do estimation using that. So this parameter epsilon is quantifying the fraction of outliers, so this is the power of the adversary. And for today, this is going to be a parameter that we should think of as a constant, which is smaller than 50%. So we corrupt at most epsilon fraction of the data. So this is a useful definition. So if there are questions on this, please let me know. Otherwise, it should be pretty standard for statisticians. All right. So, yeah, yes?
Just a quick question. So can the choice of the epsilon fraction depend on the samples?
Yes, that's what it says. Yes. So this is called adaptive contamination.
Just a quick question, because of the important talk.
All right. Okay, so the question was if the points that the adversary removes can depend on the clean samples that we draw, and the answer is yes. But even in weaker models, where this is not the case, for example, in Huber's model, the process is a mixture model. With probability 1 minus epsilon, you get a clean sample, and probability epsilon, you get a sample from an adversarial chosen distribution. So even in this weaker model, all the things I'm going to talk about are new from the algorithmic standpoint. All right, so let me spend a few minutes just being on the same page here. So how do we estimate the Gaussian in one dimension without corruptions? We use the empirical mean and the empirical variance. Everyone knows that. So these are special case of the maximum likelihood estimator. While the MLE is a great estimator, as we all know, it is not the right answer in the setting that we're considering here. It's not a matter of sample size, it's not a matter of computation, it's just the wrong problem to solve. And this was known by Huber in the 60s, even by Fisher, I assume. This kind of question, led to, it was the beginning of robust statistics, and this is the question that they ask. So what estimators behave well in the presence of adversarial contamination, in the presence of outliers? So for example, in our one-dimensional setting of robustly estimating, let's say, the mean of a Gaussian, how do we solve it? Of course, we cannot use the empirical mean. The empirical mean is terrible. Even a single outlier can completely kill its behavior, but we can use what? The median, okay? So the median is a robust estimator for the mean of a Gaussian and other symmetric distributions in one dimension. And here it's a folklore fact about its behavior. It says that the distance between the median and the true mean is going to scale like this. So there are two terms here. There is a scaling by standard deviation, as usual. The second term is what we expect, square root 1 over n. And the first term is, depends on the corruptions, on the outliers. And it so happens here that it is linear in the fraction of outliers. It's linear in epsilon. So what we observe here, so if you haven't seen robust statistics before, I know many people in this room have, this is a conceptual difference from standard estimation because there is no consistency. Even with infinitely many samples, you're not going to get error of 0. The error is going to be at least epsilon times sigma. All right, so in one dimension, the problem of robust mean estimation is easy. It's easy statistically, it's easy computationally. And then the question is what happens in high dimensions. And the immediate generalization of the problem I talked about is, can we robustly estimate the mean of a Gaussian that has identical variance? So that's the simplest version of a high-dimensional, multivariate mean estimation problem in high dimensions. And that's the goal. That's what we would like to achieve. So that's the minimax rate and it is achievable. I guess minimax, that's what it means, right? So the second term is, why is it not working? It is working, okay. The second term is what you have without corruptions, and the first term remains epsilon. So the first term that doesn't go to 0 with the samples is linear in the fraction of outliers, and it's independent of the dimension. And interestingly, this is the problematic factor. Okay, many simple things that one would do would give you a term here that is not just a function of epsilon, but also scales with the dimension, in most cases, with a polynomial function of the dimension. And this was not important in the 70s when the dimension was like 5, but when the dimension is 1 million, it's a big deal. All right, so let me illustrate the difficulty of the problem. I'm going to describe some very reasonable estimators, okay, that do not work. So the first thing one would like to do is, look at your data and do some naive outlier removal. The points that are far out, remove them. This is not going to work, unfortunately, even though it is an efficient, a computationally efficient method. The first term of the error is going to scale with epsilon times square root of the dimension. So essentially, it would give you, a mean of a Gaussian that's essentially not overlapping with the initial one. And you can try other things. Since we know that the median is good in one dimension, we can use the median in every coordinate. This also fails. We can use something that's called the geometric median. This also fails. So now, on the other hand, we have estimators that are known for a long time that are actually robust. One of them is the Tukey median. It gives you the optimal dependence on the contamination parameter, linear in epsilon, and even in the constants in front of the theta, it's pretty good. But the running time of a reasonable algorithm to compute it is really bad. So it's actually NP hard in general to compute the Tukey median. And there are other things that one can do that have similar flavor. So what we see from this table, we see that either we have estimators that are computationally efficient, so tractable, and they're very non-robust. And we have some estimators that are robust but computationally intractable. And the question we ask is whether we can sort of get the best of both worlds, get estimators that are both robust and computationally efficient in high dimensions. As we'll see, this is something that can be done, and that's the point of this talk. Now, to illustrate the difficulty of this problem, let me give you a picture here. So here's a set of points. It contains both inliers and outliers. And I promise to you that the inliers are drawn from a spherical Gaussian, and I'm asking you find the outliers. So who wants to try this? Someone who hasn't published in this area. Okay, so I mean it's I guess pretty clear that the points inside the sphere and the points outside the sphere are outliers, because we know that the Gaussian is sort of concentrated in a thin spherical shell around the mean, has radius root d, approximately root dimension. And then the question is, okay, we can detect those easily by local methods and remove them. Are there any more outliers in the data set? Are there any more? So by the way, can you hear me in the back? I'm not sure. Like in the very, okay, great, okay. So after I remove these red points, are there any more outliers?
There are observations inconsistent with the Gaussian, but that doesn't.
Okay, so, okay, tell us what you think.
There's too much mass in that.
Okay, so basically what John, who,
I'm sure that means it's an outlier.
right. So what John said is that something is looking fishy, because we know that kind of the Gaussian should be, the points should be uniformly distributed around the sphere, and these are not uniformly distributed. So what John did is he saw the picture in 2 dimensions, and he did then SVD in his mind, and he said, okay, this direction has a larger, this direction has, so basically that is the whole point. The point is that indeed in this case there are more outliers that are not obvious, in the sense that if you look at them in isolation, they're all at the right distances from the other points, but there are too many of them in a given corner of the sphere. And even though none of them is too far from the mean, none of them is an extreme outlier, combined, they really skew the empirical mean. In particular, if you compute the empirical mean of all the points on the sphere, it will be at distance epsilon times square root d far from the true mean. So these are the sort of more subtle outliers that kill us, and previous methods could not actually deal with those. All right, so the point is that distance-based pruning, naive pruning, will detect the obvious outliers, but it will not detect all of the outliers. And the ones that we do not detect can actually kill us, in the sense that the standard estimator that we would like to use, which is the empirical mean of some subset of the data, is not gonna work. So the punchline is that we were in this state until 7 years ago, and we were wondering whether it's possible to get algorithmic robust statistics in high dimensions. After we solved the problem, I found this in one of the books that Huber wrote. I'm not going to read it for you, but basically the point is that the conventional wisdom in statistics was that the answer to the question, to the algorithmic question, was no, that it's not possible to get efficient algorithms in high dimensions. And so here Huber basically does two things here. First, he says that, okay, all known methods known to him were not tractable, and he conjectures that it seems impossible to get algorithmic results in high dimensions. So in contrast with this belief, it turns out that it is possible. We cannot solve everything efficiently, but we can solve many things efficiently. So the first algorithmic progress on this question was made in 2016 by this set of authors. And I should say that most other algorithms developed subsequently, this has become into a pretty big field, rely on generalizations of the ideas introduced in this work. So the point is that we can get robust estimators that have that can tolerate a constant fraction of corrupt data. So in some sense, we actually get dimension-independent error. We get O of epsilon as opposed to O of epsilon times a function of the dimension. And I should say that some of these algorithms are, not all of them, some of them are practical and have been applied in data analysis. And while I won't have time to go over all those applications in the context of this tutorial, I'm interested more in the methodology. I will add some references. All right, so after these initial works, there has been substantial progress in the field by many groups in various communities. So here is a sample of subsequent work in unsupervised learning without references, and also in supervised learning. And a number of applications. So one of the interesting features, and one of the reasons that this work has kind of survived, because even though it's like a theoretical field, is that some of these algorithms can give you practical improvements in settings where none of these assumptions, these mathematical assumptions, are true. So here are 3 works that I have been involved with. The first one is in the context of biology, detecting patterns in biological data sets, where basically some version of robust covariance estimation can be used to detect patterns in biological data sets that are not detectable by standard methods. The second one is in the context of data poisoning, where in fact we argue that algorithms for robust mean estimation can be used for robust stochastic optimization, and we apply them in various settings. And the last one is in OOD detection, a recent work with one of my colleagues at UW-Madison. And here is a partial list of subsequent works. So an overview of these developments is in my recent book with Daniel Kane. So it's available online, so you don't need to buy it. It was recently published by Cambridge. And at this point, I kind of conclude the introduction, and I'm going to spend the rest of this first part of the tutorial explaining the ideas that are needed to get algorithmic robust mean estimation. So are there any questions up to this point? All right. So let's remember the problem. So we're given an epsilon corrupted data set, so endpoints in d dimensions. They're drawn from an unknown distribution in a known family, and the goal is to estimate the mean. So what is the most basic setup here? So what should the clean distribution be? What's the first question to look at? It is the case where the clean distribution is a spherical Gaussian, right? So what do we get in this case? So we get an efficient algorithm that approximates the mean within essentially the optimal error. So the first term here is linear in epsilon as the minimax lower bound, and the term that depends on the samples scales with the square root d over n. Now the novelty of this result is really that the first term does not depend on the dimension at all. It's dimension independent. And as a bonus, we can also get the right function of epsilon, which is linear. As you can see here, this particular theorem holds in the additive contamination model, essentially in Huber's model. It is not true in the strong contamination model. I will explain why tomorrow. Okay, but this basically says that we can completely solve the most basic version of the problem, which is robustly estimating the mean of a spherical Gaussian in Huber's contamination model. Okay, is the statement clear? So let me move on to something a little bit more general. So what happens, so this assumption of Gaussian is a little bit strong, so let's relax it a little bit. So what is a natural relaxation is the data remains spherical, the clean data, the covariance matrix of the clean data is still the identity matrix, but the distribution is not necessarily Gaussian, it's sub-Gaussian. So in this case, we get a similar flavor theorem. The only difference is that the first term is not linear in epsilon, it's almost linear. It's instead of epsilon, you get epsilon times the square root log of 1 over epsilon, which is still a dimension-independent parameter. It's only function of epsilon. And it turns out that it is also necessary. So if your family of distributions is sub-Gaussian, that's the best error that, okay, this is not very dependable. The best error that is achievable. All right? And the third theorem, which is kind of the final theorem I'm going to state today in terms of specific applications, is handling the case of unknown covariance. So far, in both the previous results, the covariance matrix of the clean data was assumed to be the identity matrix. So what happens if we do not know the covariance? So if the covariance is bounded and unknown, and this is the only assumption I'm making about the distribution, it has bound covariance. Bounded means spectrally bounded, so at most the identity in the lower order. Then we get essentially the same result, but the first term becomes proportional to square root of epsilon as opposed to epsilon. And again, this square root of epsilon dependence is the best possible you can hope for in this setting. All right, so these are three sort of specific applications for specific families of distributions for robust mean estimation. Now we will see that all of these three theorems, actually, and more, can be obtained by a single theorem that has a little bit more complicated parameters that you know will build to you know, so that it makes sense. So. Now at this point, I'm gonna start giving you a little bit of a flavor of the ideas. Are there any questions up to this point? So are the statements clear? Yes?
The second term doesn't depend on sigma?
It might be, and it's a typo. I think it should. Yeah. Thanks. Yes. So basically, the second term is what you would get without corruptions, right? When epsilon is 0. So you know, whatever that is, that's what we get. Thanks. Yeah, we're not going to prove something that's not true, right? All right, so now what are the, so I'm going to start with intuition on how, yes?
When you say it's information theoretically optimal, so you mean that there is no efficient algorithm that can achieve rate faster
Information theoretic has nothing to do with computational efficiency, as we all know. It means there's no method whatsoever. Okay. So if you're trying to estimate the mean of a distribution that is only assumed to have bounded covariance, okay, that belongs, so this is the underlying family of distributions, you cannot get error better than root epsilon. So, and this is true even in one dimension. So the reason for that is that you can construct two distributions that are both bounded covariants, so that if you add noise, different noise to both of them, then the resulting distributions are going to be identical, and the initial distributions have means that are at distance root epsilon. Okay, so since you don't know the noise, there is no way to distinguish whether the initial distribution was A or B, and the distance of the means of A or B is this, so you cannot beat this error. Make sense?
Sort of, yes, but for Tukey's median, it will give you the linear dependence.
Tukey median is not going to give you anything for
so this is not the Gaussian case, right?
Yes.
Yeah,
yes.
Okay,
for a non-symmetric distribution, Tukey median is not going to give you anything.
Okay.
This is really, the root epsilon is not a high-dimensional phenomenon. Like even in one dimension, the root epsilon is an information theoretic lower bound. Does it make sense? Okay. So. And let's explain how these things work. So I'm going to be informal for the next 10 minutes and then try to state some formal results.
Ilias, there is another question.
Oh, there is more?
Can I take
Okay.
it?
Yes,
Okay.
please.
So can I move to the previous slide? The last slide. Okay.
Yeah.
So if the covariance matrix does not have a bounded, it's not a bounded covariant, but maybe it has some special eigenstructure. For example, just the few eigenvalues is very high, and all the others are low. So can you still have some?
I mean, there are more general results
Yeah.
if the covariance is not bounded in every direction, but not in full generality. So you need to assume something about. Essentially, when you want to estimate the covariance, which in some sense you need to do here, you need some assumptions about the fourth moments.
Okay.
Make sense?
Yeah.
So there are more general results, but you need to assume more. Yes?
What are the least favorable distributions for the previous slide when you get sub-Gaussian result?
The least favorable from what perspective?
From the low bound. Why do you get this log?
Right. I mean, the point of the family of sub-Gaussians, if I take a Gaussian and I remove the tail, then it remains sub-Gaussian, right? So basically, suppose that you have this Gaussian, right? So this is the epsilon tail. This is square root log 1 over epsilon. This mass is epsilon, right? So imagine that your true distribution could be either the initial Gaussian or the Gaussian without the tail rescaled. And then if you take the truncated distribution and you add the tail, then it becomes a Gaussian. So, and basically that's it. Okay? And the point is that if you remove the tail, then you move the mean by epsilon root log 1 over epsilon. And of course, this is something you cannot do if you're working within the family of Gaussians, because you cannot play this trick, and this is why the median actually works and gives you linear error in epsilon. Any more questions? Okay, so let me go into the ideas a little bit. So I said in the beginning of the talk that, or earlier in the talk, that the empirical mean does not work for robust mean estimation. There are all these examples, but it's quite possible that it does work, right? And we want to understand some conditions under which it does. Okay, that is the first thing that sort of motivates the approach. So the key insight is that the only way for the outliers. So I'm working here with the assumption that the clean data comes from a spherical Gaussian. Okay, for the purpose of the presentation. So we have this figure where the black points are the Gaussian points and the red points are the outliers. All right? So the only way for the outliers to move the empirical mean by a lot is if they also move the covariance, to the extent that the covariance becomes significantly elliptical. In particular, it has a large eigenvalue. So that is the intuition. That is the starting point of our algorithm and any algorithm known in this domain. Here is a lemma that we're going to see later in sort of more appropriate forms. So what does it say? We get, let's say, enough samples from a spherical Gaussian. We corrupt them by epsilon, we take the empirical mean and the empirical covariance of the entire data set containing both inliers and outliers. And we have the following implication, that if the spectral norm of the sample covariance is small, then the distance between the empirical mean and the true mean is small. Okay? That is that's a formal statement. I'm going to actually prove a generalization of this very soon. Does it make sense what the statement says? So this holds with high probability over the clean points, and no matter what the outliers are. Okay, so already this gives us an idea of an algorithm, right? That somehow we look at the data set, we compute the largest eigenvalue of the empirical covariance matrix, which we can't do efficiently, because it's a miracle that eigenvalue computation can be done efficiently, even though it's a non-convex problem. If it so happens that the largest eigenvalue of sigma hat is not too large, then we just use the empirical mean. Okay? But of course, the difficulty is what happens if it is, because for example, you can have the previous example where these outliers are not kind of obvious to detect and remove. And if they're there, certainly there will be a direction of large variance. So this method of just output the empirical mean does not work. Now, a useful idea that is going to come into the proof of this lemma is that we're working with distributions that have the property that if you remove any small fraction of the clean data, it's not going to bias the statistics by a lot. In particular, if you have a Gaussian sample and you remove an epsilon fraction of the points, any epsilon fraction, then the mean and the covariance are not going to move by a lot. And this is an important insight that used both for the proof of this lemma and for the algorithms. And the algorithmic idea is that we're going to try to handle the case where the empirical covariance has a large eigenvalue, is to somehow remove outliers, not in one shot, but in many iterations, to fix the empirical covariance. Okay, so that eventually we get a subset of the entire data set that has a large overlap with the clean data, and the empirical covariance of the final data set is going to be small. So in some sense, we can apply the lemma, the previous lemma, to say, okay, I'm going to output the empirical mean of that data set. So can someone tell me what's the gap with what I just said? I mean, there's an obvious gap, and the gap is as follows, that when we do the outlier removal procedure, we will also end up removing a small fraction of the clean points. This is unavoidable. If we do that, then the final data set we're going to have is not going to be a clean Gaussian sample plus very few outliers. We have removed some of the clean points. So we need something more general than what I said in the previous slide. So this is a method that we call iterative filtering. So it's a two-step procedure with an iteration. And it doesn't work only for the mean, it works for many other problems, but I'm going to illustrate it today for the mean. So in the first step, we have some kind of certificate of the standard estimator for the mean. The certificate is just, we look at the empirical covariance and check if the largest eigenvalue is small or large. And in the second step, if the certificate is not satisfied, so if the largest eigenvalue is large, then we use this fact to detect and remove many outliers. And in the process, some inliers as well that we have to control. All right, so here is what we do when there is a large eigenvalue. Here's a picture. So suppose that sigma hat has a large eigenvalue. So the one is what it should be without outliers, and the second term, all right, this is not working officially. The second term is kind of the deviation from what you expect. Then the idea is that if you project the data in a direction of large variance, let's say the direction of largest variance, then it's going to look like this. So you have two bumps on the top. So the leftmost one corresponds to the clean data, and the rightmost one corresponds to the outliers. And the second picture is basically just the projection of the points in the v direction, so all of them should be on the line. So looking at it, so first of all, why should the picture be like this? Like by assumption, we know that the outliers move the covariance significantly in this direction, so the variance is significantly bigger than 1, and the outliers are a small fraction of the data set, an epsilon fraction of the data set. So on average, the outliers have to be far from the true mean, which in this case is here. All right, so looking at this picture, what would you do to estimate, to remove outliers? Okay, I see John's hand, he did this. So I don't know what it means, but I assume it means this, right? So, it's intuitive, right, to find the threshold t, and then everything that's above the threshold, remove it. And this picture is quite illustrative. So if we do that, then we remove both red points and black points, okay? But the important things that we can control, the relative sizes. We remove more red points than black points. And because the number of red points is small, because we started from an epsilon fraction of outliers, the number of black points we also remove is also small throughout the iterations. Therefore, overall, the final data set will remove all the significant outliers and a small fraction of the inliers. So that's the sort of most intuitive version of this algorithm. This procedure actually works, at least for the Gaussian and some other cases. And here is a pseudocode that you can ignore if you like. But the point is that there is a formula, efficiently computable, to find this threshold t from the previous slide. And the formula relies on the violation of a concentration inequality. We know that the clean data projected in this direction, in any direction, satisfies the Gaussian concentration inequality. And the point is that the outliers cannot satisfy the same inequality. They need to value this inequality, because if they didn't, then the variance in this direction wouldn't be large. So this gives us a way to find this threshold, and then we remove points in the obvious way and iterate. So that is the first version of this filtering algorithm. And the analysis, intuitively at least, is not that difficult. So, of course, the running time of the algorithm is going to be polynomial, because in every iteration you remove at least 1 point, and you have a bounded number of points or even outliers. And in terms of correctness, you need to argue that this process does not eat up the entire data set, and also that it removes more outliers than inliers. And this is the second claim, which is obvious from the picture, but not obvious in general. So eventually, we're going to have a subset of the initial data set that has a large overlap with the clean data, and doesn't have any large eigenvalue, and then we can output the empirical mean of that subset. So that is the algorithm, and it's an efficient algorithm that gives us the error that we wanted. Are there any questions?
So you assume you know X.
Okay, I think I've heard this question okay, the question was whether we assume with no epsilon. For this talk, yes. For most of these problems, we don't need to, unless it's actually necessary. So there are some situations where you need to know epsilon information theory. For example, if you have a distribution that has, let's say, bounded variance, even in one dimension, and you corrupt an epsilon fraction of the data, if you do not know the bound of the variance, you need to know epsilon. Information theoretically, otherwise you cannot do anything. Okay, if you know the bound of the variance at most 1, then you don't need to know epsilon. So this is sort of presented here for convenience, but these algorithms do not need to know epsilon. This can be done by changing the code itself, or also in a black box way by running the algorithm many times for various guesses of epsilon and outputting the best answer at the end. Right? All right. So now I'm going to be a little bit more formal in the next 15 to 20 minutes. So I want to formalize these ideas, and I haven't done this before in a talk, so let's see how it goes. I've done this in class. So I'm going to define the deterministic condition, okay, under which this algorithm, or some version of this algorithm, actually works. So this is the stability condition. So the point, what we're going to see is that robust mean estimation algorithms are going to work as long as the inlier satisfies the stability condition. It's a little bit maybe technical, it's like a few lines, but what it says is that a set S, a finite set S, is epsilon delta stable. Epsilon is usually related to the fraction of outliers. It might be a constant factor larger for technical reasons. Delta is a second parameter that is at least epsilon. It's significantly larger than epsilon. And what we want is that removing any epsilon fraction of the points in S will not change the mean by more than delta, and will not change the variance in any direction by more than delta square over epsilon. So I want to stay here for a minute so that we pass this condition. I mean, the first condition is kind of clear, right? It just says that removing an epsilon fraction of the points doesn't move the mean by more than delta, all right? Or delta is some parameter. The second condition says that essentially, if you look at the spectral norm of the empirical covariance minus the identity, then this is also going to be small. And how small? It is delta square over epsilon, because this is the right scaling. So are there any questions about this definition? I mean, I would have some questions if I saw this written somewhere. Like one question, for example, is why, okay, you have?
What is delta here?
Delta is some parameter. Epsilon and delta are parameters, okay? Delta eventually is going to be the final error we achieve in the mean. But you know, this property is parameterized by epsilon and delta, epsilon delta stability. You're going to see what delta is in the next slide. Okay? But like one obvious question is like, why the 1? Why are we subtracting 1 in the second stability condition? So why are we insisting that the empirical covariance is close to the identity? And the answer to that is that this is specialized for robust mean estimation of distributions that have covariance equal to the identity or less than or equal to the identity. If we had a different bound on the covariance, instead of 1, we would have or instead of the identity matrix, we would have the corresponding matrix there. And the third bullet is important. The point is that you should think of a stable set as, it's not always the case, but you should think of it as a set of clean samples from a well-behaved distribution. For example, one can show that if you take enough samples from a Gaussian, then with high probability it's going to satisfy this condition for delta being basically what you get by removing the tail, which is epsilon times square root log 1 over epsilon. And a similar fact holds for many other families of distributions. So this gives us a unified way of robust mean estimation without considering specific distribution families, but just these properties. So here is a theorem, or the sort of general theorem that implies the theorems from the previous slides. So it says that if S is a stable set with parameters epsilon and delta, and T is a corruption of S, an epsilon corruption of S, meaning that T is obtained by corrupting an epsilon fraction of the points in S, then we can efficiently estimate the mean within error which is proportional to delta. So this is delta. That's the answer to your question. So delta is basically the final error that we get for the mean. And now what is this parameter delta for various families of distributions? Here it is. So if we have Gaussian samples, then delta is epsilon times square root log 1 over epsilon. If we have sub-exponential tails, then it's epsilon times log 1 over epsilon. If we have bounded kth moments, where k is at least 4, delta is epsilon to the 1 minus 1 over k. And if we only have bound covariance, then delta is proportional to square root of epsilon. So just by applying this general theorem for all these families of distributions, we get the bounds we saw in the previous slides and more. Any questions about this slide? All right. So let me now give you the sort of most important property of stability. So why do we define this condition? We define it because it allows us to actually certify that the empirical mean of a corrupted version of a stable set is going to be close to the true mean if there is no large eigenvalue. So let me parse this theorem. So let S be a stable set. T is an epsilon corruption of this set. Then if the empirical covariance of T has largest eigenvalue at most 1 plus lambda, then the distance between the empirical mean of T and the true mean scales like this right-hand side. So it's delta plus the square root of epsilon lambda. Again, I'm going to actually give you the proof of this. It's basic linear algebra. So if we consider the uniform distributions over the sets S and T, so discrete distributions, then we can consider Y to be a mixture between X prime and E, where E is the distribution of additive noise. So where X prime is obtained from X by removing an epsilon fraction of the mass. Okay, and the point is that the mean of Y is the mean of T. Okay, just by the definition of the contamination model. So I'm going to use the fact that the covariance matrix of T doesn't have any large eigenvalues. So to do that, I'm going to write down the covariance of T as a function of the covariances of X prime, of the covariance of E, and the corresponding mean. So we get the two linear terms and the cross term. Nothing deep is happening here. And now what I'm going to do is I'm going to use the definition of eigenvalues. So for any direction V, for any unit vector V, so V transpose sigma T V is at most what? It's at most 1 plus lambda by assumption, right? Because we assume that the spectral norm of sigma T is small. And by the formula above on the covariance matrix of Y, we can write down what this quadratic form is. It has three terms. So what can you tell me about each one of those terms? I'm trying to bound this quantity from below. So what can I say about each one of these three terms? What can I say about the middle term, the one with sigma E? So it's certainly non-negative, right? Because sigma E is a positive semi-definite matrix. Okay? It comes from the additive noise. So this is non-negative. The last term is basically, the distance between mu x prime and mu e squared, because I picked V to be parallel to this direction. And how about the first term? So V transpose sigma x prime V. Okay, great. So basically, by the second stability condition, this is not too small. It's at least 1 minus some error, and the error comes from the stability, and this error is delta square over epsilon. So I get this inequality. Okay? And after that, I just rearrange and get that the distance between the mean of x prime and the mean of E is going to be at most this. So we're not quite done. So what I'm interested in is the distance between the mean of T and mu. So how do I do that? Well, I just write down what the mean is, just a linear combination of the two means. So the distance between the mean of T and mu is equal to this difference by triangle inequality. It can be written like this. So what do I do now? The second term has been handled, so mu x prime minus mu e, by the above. So how about the first term? Mu x prime minus mu. Can you also tell me? So by the first stability condition, it's going to be order of delta. So this completes the proof. And this is the lemma that we need to use throughout the iterations of the algorithm, because by the outlier removal procedure, we are going to remove some inliers. So the important property that we have is that every intermediate subset of T that we have in the current iteration is a corrupted version of a stable set. All right, so let's see how much time I have. Not much. All right, so the next idea I want to introduce is filtering points in a randomized way. So what we did so far, we consider filtering just by violation of the deterministic of a concentration inequality, which is not good enough in some more general settings. So this more general idea of randomized filtering works as follows. The idea is that if we find a function f, which is non-zero, defined on the data set, and this function has the property that the sum of the values of the function over the entire data set t is at least twice the sum of the values of the function over the inliers or a stable set, then we can remove outliers randomly by taking every point in the data set t and removing it with probability that's proportional to the function of f of x. And this ensures that in any given filtering iteration, the expected number of outliers removed is at least the expected number of inliers removed. Okay, so that is the idea of randomized filtering. And of course, for this to work, such a function f must exist. So I must exhibit that this can be done. But if I have such a function, then it's possible to actually implement filtering under the stability condition in a more principled way. One issue is that the way this condition is written only for the initial corrupted set t, while we want it to be true for in any given iteration of the algorithm. So we need some more general condition, which is this one. Right? So let me just give you the pseudocode, okay, and maybe conclude in a few minutes. So here is the here is the pseudocode. So we start from the set T, the initial corrupted set. We calculate the largest eigenvalue, and we pick some threshold lambda. Appropriately, lambda in this slide is a parameter. So if this maximum eigenvalue is at most 1 plus lambda, then we just output the mean of the empirical mean of T. Otherwise, we compute this function f. It needs to be efficiently computable. And then we remove each point of the data set with probability f of x divided by the maximum value of f of x. We get a new set T, and we iterate. That is the algorithm, and it works under the stability condition. So are there any questions about the method?
Where do you get lambda?
So lambda is a parameter now. At the end of the method, we need to set it to a specific value. So let me go back. So the point is that I'm assuming for this algorithm to work that there exists a function f that satisfies this property. We're going to show that this function only exists if this parameter lambda is sufficiently large. And large means something like delta square over epsilon, where epsilon and delta are the stability parameters. So this function f does not always exist. It only exists if the largest eigenvalue of the empirical covariance matrix is sufficiently large, and this quantity determines what lambda should be at the end. Okay, so far, lambda has been a parameter. All right, so I was thinking of analyzing this. Is there? Oh, sorry.
So how should we be thinking about the filtering function f and where it's coming from? It sort of seems magical right now.
It is because I haven't told you what it is. Okay,
right.
But I can state, okay. So I'm going to skip the analysis of this method, which I wanted to actually give you, because it uses Wille's maximal inequality, and Wille was born in Marseille, but in any case, so let me tell you what this function is. Okay, this function f. So intuitively, right? So we are. Remember what we did in the initial filter, right? So we found the largest eigenvalue, projected the data there, and we looked at the projections, and based on that, we removed points. So a reasonable way to pick this function f is to do the same thing, like find the largest eigenvalue of the empirical covariance, and calculate this function. So what is this function? So g of x. It is the contribution of point x to the variance in the v direction. Yes? So a point that has large contribution to the variance is more likely to be an outlier, so we should remove it with larger probability. So intuitively, we should take this function. Unfortunately, this doesn't work. So what we actually do is we only take the top epsilon fraction of those points, and then we only use those. So this is the function f. Okay, this is something that you can compute efficiently. So you have the set t. You can compute the mean, you can compute g of x, So you can compute the mean, you can compute V, which is the largest eigenvalue of sigma t. You can compute the function g of x, then you put the points on a line, you order them, and you pick the largest fraction, and this gives you the function f of x. And this is the function that we use for randomized filtering. Now, there are other functions one can use, but this is one that is kind of easier to analyze. So by putting these two things together, we have the randomized filtering algorithm, and that concludes sort of the technical part. I don't think I have enough time to go into the proofs, but maybe I have like 4 or 5 minutes because we started a little bit late. So if you want to see that, so there were 2 proofs here. One was that the randomized filtering works, and the other is that this particular function, f of x, works. I'll put the slides online, but if you want to see them, I can describe them in 10 minutes tomorrow. So the last thing I want to say is that instead of removing points randomly, another thing to do, which is conceptually equivalent, is to assign weights to the points, where the weight quantifies whether we believe it's an inlier or an outlier. If it's 0, it means it's an outlier, we're certain. If it's 1, we're certain it's an inlier. If it's something in between, it basically quantifies our confidence in that. So there is a version of randomized filtering with weights, which is very similar. And the important thing that I want to say here is that there is a well-defined optimization problem when you work with weights that is enough for robust mean estimation under stability condition. And this optimization problem is this one. So we take this convex set delta. This convex set is basically the convex hull of all possible subsets of your initial data set that contain 1 minus epsilon fraction of the points. And the optimization problem that you want to solve is find a weight vector in this set delta that minimizes the spectral norm of the weighted covariance. So if you solve this problem and you find the W that it gives you, then you can use the weighted mean weighted by this W, and that always works. That is really the punchline for robust mean estimation under the stability condition. So you just need to solve this problem, and all of the algorithms that we have described and all the algorithms that there are out there actually solve this problem in some form. For example, when you actually remove points, then the W is going to be discrete, but in general it doesn't need to be. Okay, that's like the one thing to remember. You just need to assign weights to the points so that the weighted covariance has no large eigenvalue, and if you do that, then you're done. And it turns out that even though this optimization problem is non-convex, it can be solved by gradient descent. So you can just run vanilla gradient descent on this objective, which is non-convex. It's going to give you a stationary point, and no matter what stationary point it gives you, it's good enough. So at this point, structurally, we understand robust mean estimation quite well. This is not the case for more complicated problems. When you go to covariance and higher moments, there are like more subtle phenomena. So let me give a few open problems and conclude. I'm going to just show them here. So the algorithms I have described are not necessarily near linear time. They work in polynomial time, but not necessarily linear. One direction is to get fast algorithms, so as fast as possible. We have n points in d dimensions. N times d is the size of the input. Ideally, we would like to solve robust mean estimation in this time. Okay? We can do this in many cases, but for more general problems, in particular in the context of sparsity, there's still significant gaps. Another direction that I like is, can we sort of have a deeper connection between non-convex optimization and robust statistics? So basically what I just described a minute ago for the mean, but in more general settings. And finally, can we do all of these things in low memory? So these algorithms I have described actually need the entire data set in memory. Can we do this by just having one sample in memory, in a streaming setting, in a streaming and single pass? So there is some progress on this, but we still haven't solved the problem, and I suspect that in some regimes there are inherent trade-offs between the sample size and memory. And finally, consider this is not even well defined. So can we actually go beyond the statistical setting, or at least the purely statistical setting, and do robust estimation in some kind of online regime? Now, even to define this problem is unclear. It depends on your application, but I think this would make robust estimation more practical if it actually works in an online regime. And at this point, I'm going to conclude the first part of the talk and take questions.